All right, so let's go ahead and start with example 2. Again, example 1 was building all the previous theory. And again, I'll go ahead and use blue. You know what? I use blue for a lot of things, so I'm going to use purple as my writing tool here. So let's go ahead and create the characteristic equation. And every time you're going to do this with a Cauchy-Euler, and this is definitely Cauchy-Euler, as you could see here via the exponents versus the order of the derivative, what we're going to do is go ahead and build the characteristic equation. So let's do that. Characteristic equation, again, we're going to let or assume that our solutions are of the form y equals x to the nth power. Well, if you take two derivatives of that, well, let's take a first derivative. First derivative will be mx to the m minus 1. The second derivative, that's first derivative. The second derivative is m times m minus 1, x to the m minus 2. And you insert those into your Cauchy-Euler differential equation, and you will arrive at the following: x squared times the quantity m times m minus 1 to the x times x to the m minus 2 plus 3x, again, times the first derivative, which we're saying is mx to the m minus 1. And then finally, minus 4 times y itself, which we're assuming is going to be x to the mth. All of these, if you multiply the x's through, will have x to the mth, and you'll get down to x to the nth power times the quantity m times m minus 1 plus 3 times m minus 4 is equal to 0. And you should do this, I think, every single time. It's my opinion you should do this every single time when you're solving a Cauchy-Euler differential equation. Just build these equations. Let me highlight them so we can see them. Build these equations right here and insert them into the differential equation, because trust me, you will not, or it's not readily or easily done to memorize all the forms you're going to see, so it's much easier just to do this. So we, again, will just discount that guy right there because it's not going to really turn this product into 0 unless x is 0 itself. And we arrive at the following characteristic equation: m squared, and let's see, I have 3 of these m's, but I'm losing one of them here, so I have plus 2m minus 4 is equal to 0. Which is very nice, a nice clean format. I could solve that. It's not factorable, but that's okay. M is equal to the opposite of that 2, plus or minus the square root of that 2 squared, minus 4 times the coefficient of m squared times the constant, all over twice the coefficient of m squared. And cleaning that up, it's just negative 1 plus or minus. And underneath that square root, the discriminant, you'll have a 4 plus 16, or a 20. And the square root of 20 is going to be 2 times the square root of 5. The 2's cancel, so it's plus or minus root 5. So I have 2 real roots here, actually, which tells me that my solution is going to be y sub c. I always use the subscript c if I'm solving just homogeneous, just because it plays well with the rest of our theory. So the complementary function y sub c is going to equal c sub 1 x to the negative 1 plus root 5 plus c sub 2 x to the negative 1 minus root 5. So here is an example of solving, example 2 here, is an example of solving a Cauchy-Euler differential equation that's homogeneous, which results in a characteristic equation with 2 real roots, and that results in a solution that's pretty simple, actually, right? You just take each of the roots as the powers for your base x in your solution.